Hello everybody, it is a pleasure to present our research titled Parametric Statistical Scheme for Tracing the Transmission of Total Harmonic Distortion between a Power Network Analyzer and an Oscilloscope. This work addresses a crucial methodological challenge in the field of power quality. The traceability of total harmonic distortion, or THD, measurement is fundamental for confidence in the results of any measurement. Uh, Through this presentation, we will explore a non-standardized methodology that allows the transfer of metrological traceability from a widely calibrated reference instrument to a power network analyzer. Okay, so the starting point of our research is a practical problem in many countries in Central and South America. The difficulty in accessing accredited laboratories, particularly in the standard of the calibration 17025, in the calibration for power network analyzers. This is not common in our countries, so this is a problem because these devices are essential for measuring power quality, including voltage total harmonic distortion. This work is about the voltage total harmonic distortion, uh, which visually manifests as a deformation in the pure sine wave, as you can see in our diagram, right? Um, well, well, while the network analyzers lack accredited calibration options. Um, on the other hand, oscilloscope have a wide range of traceability calibration options. So our proposal focus on leveraging this existing traceability in the oscilloscope to transfer it to the network analyzer, thus closing the metrology gap. So, so the core of our work is this parametric statistical scheme, which is developed in five main phases. First of all, controlled THD in voltage generator. We need a system that can deform the voltage wave in a controlled and reproducibility manner to generate a specific calibration point. Second phase, simultaneous measurement. This is a challenge because the reference oscilloscope and the analyzer under calibration simultaneously measure the same distorted signal in the same time. Uh, the third phase, statistical stability analysis. Before calibration, it is imperative to validate the stability and the reproducibility of the THD voltage generation system. We need to check that if we do this the experiment anytime, I will take the same results. In the fourth phase, uncertainty estimation, about the guide of uncertainty measurement um, suggested by the Bureau, the International Bureau of Weights and Measurements. Uh, so we applied the guide to the expression of uncertainty measurement to characterize the system uncertainty. And the last phases, direct comparison calibration. Finally, the calibration relationship in the traceability, in the transfer of traceability from the oscilloscope to the analysis network are established. So for the first step, we designed a THD voltage generation using a low-cost, high-ability component. Um, the diagram shows the heart of the system, an Arduino Mega microcontroller that acts as the control brain. The key components are the optocoupler for precise zero crossing detection of the continuous voltage, the voltage wave, the uh, optocoupler MOC3021. This act as a solid state with switches to chop the voltage wave and a resistive load to simulate a nonlinear load. Yeah? The design allows for controlled and insulated deformation of the wave, which is crucial for generating stable calibration points. Uh, so, the principle of operation is based on phase control. The microcontroller uses the zero crossing signal as a trigger to introduce delay, or a delta t, before fueling the triac. The diagram illustrates how this delay results in a symmetrical chop of the wave in the positive and negative half cycles. By varying this delay time, we control the portion of the wave that research the load, which in turn generate different levels of total harmonic distortion. The experiment control range was set between 1000 microseconds to 2000 microseconds, allowing us to generate a spectrum of THD and voltage values calibration. Yeah? A crucial step in data processing is the conversion of oscilloscope measurements. Processing the oscilloscope calibrated signal in a MATLAB gives us the THD voltage in decibels. To compare it directly with the network analyzed results, which given in percentage, we apply the transform between percentage to decibels. The equation allows the conversion from decibels to percentage in an easy way. It's important to know that for the uncertainty estimation, we rigorously follow the methodology established in the guide to the expression of uncertainty in measurement and international standard in metrology. This is important because we need to check the parametric or no parametric statistics that we should use. So, the validity of the calibration depends on the stability of the generation system. We performed 3 statistical tests to confirm this. The Ryan Joyner to check the normality of the data. If we pass the Ryan Joyner test, we can use parametric statistics. That is the objective of the paper, because if we don't have a good Ryan Joyner test, we can't use the parametric statistics, and we should do a no parametric chain. The null hypothesis in this test, that the data follows a normal distribution, was accepted with a p-value greater than 0.1. Next, we applied the graphs test to check the absence of outlier. The null hypothesis that no outlier exists was accepted with a p-value of 0.1. Then the Bartlett test was used to check the homogeneity of variance. The null hypothesis that all the variants are statistical equal, so that hypothesis was also accepted. So the conclusion is clear. The system is stable and reproducible, and at 95% of confidence level, with the maximum observed variability was 1.02 percentage, and it was incorporated as an additional uncertainty source in the model, the variation of stability of the chain. Traceability transfer is achieved through uncertainty characterization. The central equation is the combined uncertainty model, mathematical model, and this model allows us to propagate the uncertainties of the primary source to the final measurement. The main uncertainty source we characterized came from the reference oscilloscope, the horizontal deflection, 10 bias, the vertical deflation. We add the chain validation and any other uncertainty source. And the final objective is to use this no uncertainties source from the oscilloscope to characterize the uncertainty of the network analysis, thirdly, achieving metrology traceability. Um, with the uncertainty estimation, we also to check a new model to determine a percentage of uncertainty in the analyzer under calibration. In conclusion, the proposed method proves to be a viable and effective solution for transfer metrological traceability. The process is summarized in four case steps: controlled TH voltage generation, reference measurement with a calibrated oscilloscope, and the test measurement with the network analyzer, and traceability calculation using the guide on uncertainty measurement, adding the corrections and the uh, percentage of stability. This is a non-standardized approach offers a practical and rigorous alternative for countries without access to accredited laboratories in calibration of network analysis. But we can use this to check verifications, and we can it was allowing power network analyzers to operate with a confidence of and metrological precision required by power quality regulation to check measurements about the behavior of any network of electrical energy. Thank you very much for your attention. It was a pleasure.